In the last lecture, we were examining unidirectional transport, that is transport in one dimension, in this particular case in a Cartesian coordinate system. And the first example we considered was the thermal diffusion from a surface that is located at z equal to 0 into an infinite medium in which the temperature was T infinity far from the surface, and initially the temperature is T infinity everywhere, and at time T is equal to 0 the temperature at the surface itself alone is increased to T equals T naught. Okay. So, initially the temperature is T infinity everywhere in the medium except at the surface where it is equal to T naught. Because of the temperature difference, there is diffusion of heat, and therefore, the temperature increases as a function of time within the medium. Okay. So, it will have different forms. At early time it will look like this, and at much later time it will look like this. So, as time increases, you see this progression. Diffusion equation unsteady in we had first defined the scale temperature as T star is equal to T minus T infinity by T naught minus T infinity, which means that T star is equal to 1 at the surface, T star is equal to 0 far away. And the diffusion equation in terms of the scale temperature is partial T star by partial T is equal to alpha d square T star by partial z square. Okay, so, that was the thermal diffusion equation. In this particular case, since we have diffusion into an infinite medium, we had used the fact that there is no length scale in the problem by which I can scale the z coordinate. There is no time scale either, time goes from 0 to infinity. Therefore, I can get only one dimensionless group consisting of length and time, z by root alpha t. Okay. This is the only dimensionless parameter in the problem. Okay. Therefore, I express T star in terms of psi, okay, so by using chain rule for differentiation for psi as a function of z and as a function of t. So, basically we wrote partial T star by partial z is equal to partial T star by partial psi by partial z. If it is dependent only on a single variable, then I should write this as the total derivative, and similarly partial T star by partial T is equal to dt star by dz partial psi partial psi by partial t, and so on, and we had used this to solve the problem. Okay. Expressed in terms of psi, right, expressed in terms of psi, the boundary conditions are T star is equal to 1 at psi is equal to 0, T star is equal to 0 for psi going to infinity. This second boundary condition contained both the initial condition and the boundary condition for z going to infinity. Both of these reduced to just one condition, okay, and therefore, we were able to solve the problem. Okay. The solution we got was of the form T star is equal to 1 minus error function of psi by 2, okay, where error function of x is equal to 2 by root pi integral 0 to x dx prime e power minus x prime square. Okay. And if I plot this as a function of x, okay, this is equal to 1, I get something that goes like this. And based upon this, I had derived an expression for the heat flux Qz, okay, is equal to minus k partial T by partial z. expressed in dimensionless form minus k by root alpha t, okay, times into t naught minus t infinity partial t star by partial psi. Okay. And the heat flux at z is equal to 0 is equal to minus k into t naught minus t infinity by root alpha t partial t by partial psi at psi equals 0. This one turned out to be minus 1 over square root of pi. Okay. So, this turned out to be, I had shown you in the last class, this is minus 1 by root pi. The constant C in the equation that we had, C1 in the equation for the temperature field, was minus 1 by root pi. Okay. And based upon this, we had got the temperature, the heat flux as minus k into t naught minus t infinity by root of pi alpha t. Okay. So, that was the expression for the heat flux as a function of time. I had discussed this root of alpha t as physical interpretation as a penetration depth. When z is much larger than root alpha t, there is no disturbance to the temperature due to the heating from the surface. There is a disturbance to the temperature due to heating from the surface only when z is comparable to root of alpha t. And this penetration depth scales proportional to square root of t as time progresses. If the length increases proportional to square root of alpha t, then the gradient has to decrease as 1 over square root of alpha t, because the gradient is a temperature difference divided by a length. Okay. And therefore, the heat flux decreases proportional to square root of alpha t as time progresses. Even though this seemed an idealized problem, okay, even though this seemed an idealized problem, I showed you, because normally you will not have an infinite system. Okay. So, I showed you conditions under which this can be applied for a finite system, so long as the system size h in the heat flux direction. Okay. So long as the system size h is much larger than the penetration depth, you can still assume that the boundary condition is to be applied as t goes to infinity. Okay. The other problem that I talked about was that if we have a falling film, okay, of fluid, okay, I will consider this as the z direction, this as the x direction. Flow direction is the x direction and the cross stream direction is the z direction. Okay. At z is equal to 0, the fluid is brought into contact with a gas such that the concentration at the surface is Cs, and we assume that the concentration within the film is 0, okay, there is no gas there. The velocity profile looks something like this. It is a parabolic profile, okay, with 0 velocity at the vertical wall, 0 velocity at the vertical wall due to the no slip condition, and 0 velocity gradient at the free interface, 0 velocity gradient at the free interface, because there should be no shear stress at an interface between a liquid and a gas. Okay, there should be no shear stress at the interface between a liquid and a gas. And we had considered the limit where the penetration depth was small compared to the thickness of the film. Okay. So, that within this region close to the surface, you have what is basically a falling film, okay, falling at nearly a constant velocity. This is the maximum velocity, okay, and you have diffusion of material in, okay, due to the concentration at the surface. Okay. Now, in this configuration, okay, I can identify, right. So, the film is falling downwards and there is an increase in concentration into the film, okay, due to the surface concentration. The concentration equation is partial C by partial T is sorry. Okay. For the unsteady problem, it was partial C by partial T is equal to D partial square C by partial Z square. Okay. And if I just define C star is equal to C by Cs, I just get this in terms of C star. This is a steady problem, but it is varying in the x direction. Okay. So, for a parcel of fluid that is travelling downwards, I can identify the time of contact as the ratio of the distance travelled divided by the velocity, okay, where V max is the maximum velocity. Okay. V max is the maximum velocity. Okay. And for a falling film, we know that V max is equal to 3 by 2 times the average velocity. Okay. So, this relationship is known for a falling film if you have a parabolic velocity profile. Okay. So, this will be x by 3 V average by 2. Okay. So, rather than looking at it as time progresses, you are looking at it as the parcel of fluid is travelling downwards and the time of contact increases, and that time of contact is just given by this one. Okay. That time of contact is given by this one. Okay. So, therefore, equation is the same, except that the time has been now replaced by the distance travelled divided by the velocity of the surface of the film. Okay. Therefore, I can get an expression for the flux J z, okay, similar to the q z that I had here. Okay. I am sorry, I should note that this q z, there is no negative sign here, okay, because this is minus 1 by root pi and there is a negative sign here. Okay. So, analogous with this expression, okay, I can write an expression for the flux, okay, is equal to the diffusion coefficient instead of the thermal conductivity into Cs instead of the temperature difference by root of pi d, okay, diffusion coefficient into T, which is x by 3 V average by 2, okay, the square root of this whole thing. That is J z, that is the flux locally at a given position x, okay, at a given downstream position x, this is the flux. Okay. You can get the average flux. Let us say that the total contacting section had a length L. Okay. Let us say that the total contacting section had a length L. Okay. Then the average flux is equal to 1 over L integral 0 to L, okay, dx times J z. Okay. And within this expression, the only term that depends upon x is this one. Okay. So, if you do the integral, okay, you will get this as d Cs by root pi d into 2 by 3 V average, okay, integral 0 to L dx times x to the half. Okay. And you can do this integral, it is basically 2 times L to the half. Okay. So, based upon this, what I will get is that this J average is equal to d Cs by L into root of 3 V average by 2 pi d into 2 L power half. Okay. That is the average flux. Okay. So, that is the average flux over the, if you average it over the streamwise direction. Okay. This is usually expressed in terms of a correlation. Okay. Rather than writing the average flux, you define the Sherwood number is equal to J average by d Cs by L. Okay. J average by d Cs by L. This is the characteristic flux, the denominator is the characteristic flux for diffusion coefficient d, concentration difference Cs and total length scale L. Okay. And so, this you will get it as root of 6 by pi, okay, into V average L by d whole power half. Okay. This term here is what is called the Peclet number, the ratio of convection and diffusion for mass transport. Okay. The Peclet number, the ratio of convection and diffusion for mass transport. This Peclet number is defined in terms of the length scale L, the total length of the film, under the assumption that the penetration depth is small compared to the height. Okay. So, this will give you root of 6 by pi times P E L to the half. Okay. And this Sherwood number is also based upon the total length L. Okay. So, this can be used for determining the correlation between the Sherwood number and the Peclet number. Okay. I should note that it matters what length scale you use. Okay. If you happen to use the height as the length scale, okay, if you happen to use this height as the length scale, then you would get a different answer. Okay. The Sherwood number defined based upon height is equal to J average by d Cs by h. Okay, which will be equal to root of 6 by pi into V average by L by d power half divided by this will be into Peclet number based upon h power half into h by h by L whole power half. Okay. Okay. So, this is what you would get if you wrote it in terms of the thickness, whereas the correct way to write it is in terms of this length scale L, because the contacting is happening over the length scale L, and the thickness of the penetration depth is also determined by the length scale L. Okay. So, that is the correct way to write it. So, this is an example of how you get a Sherwood number correlation, okay, for in terms of the Peclet number and for the film flow. We will see more of this when we do boundary layer theory later. Okay. Okay. So, this is for diffusion into an infinite medium. Okay. I will go to another problem on diffusion in infinite medium, where we will once again use similarity variables, but of a slightly different kind. Okay. So, this is the decay of a pulse. Okay. So, what is this? So, let us take a one dimensional problem where I have this is x, this is z, infinite fluid both above and below, okay. And at time t equal to 0, you release a certain mass per unit area, okay, a certain mass per unit area along the plane, okay, m, okay. At the location z is equal to 0. In 3 dimensions, this would be like releasing some pollutant at a particular point, a certain mass of pollutant at a particular point. Okay. This is we are considering in 1 dimension, where you are releasing it at a particular location. Okay. And so, if I plot the concentration field for this, right, initially there will be 0 concentration everywhere. So, let me just slightly. If I plot the concentration field for this, initially there will be 0 concentration everywhere, except at this point where the concentration diverges, because you are releasing a mass within an infinitesimal volume. Okay. Mass per unit area is being released within an infinitesimal interval in the spatial coordinate. As time progresses, this will spread. Okay. As time progresses, this will spread. Initially, it will be very close to the origin, then later it will diffuse more, and then at very long time the maximum will become lower and the extent will become larger. Okay. So, what we want to understand is how does this concentration spread with time. Okay. So, of course, the diffusion equation partial C by partial T is equal to d square C by dz square. Okay. You know that as z goes to plus or minus infinity, the concentration has to go to 0, okay, because that is an undisturbed fluid, undisturbed medium. Okay. So, C goes to 0 for z going to plus or minus infinity. Okay. However, there is one other condition here, and that is that the total mass released initially, right, the total mass that has been released initially has to be the same as the mass at any instant of time. Okay. The total mass released initially has to be the same as the mass at any instant of time. Okay. The mass released initially, right, the total mass released initially per unit area has to be the same as the mass released at any instant of time. Okay. The total mass within the medium at any instant of time. The total mass within the medium at any instant of time is dz times C, okay, which is in turn a function of z and t. Okay. So, the mass released initially has to be the total mass at any instant of time. Okay. Note that I told you m is a mass per unit area, C is concentration, mass per unit volume. So, if I integrate C over a length, okay, over the length coordinate, I will get a mass per unit area. Okay. Okay. So, this is the problem that we have to solve. Okay. So, this is the problem that we have to solve. Okay. Once again, okay, we can of course, there is no length scale in the problem, right. You are releasing the mass within an infinitesimal interval, okay, interval tending to 0, okay, and then you are applying boundary conditions at plus or minus infinity. So, there is no length scale in the problem. Okay. So, what that implies is that I can use a similarity transform psi is equal to z by root of dt. Okay. Psi is equal to z by root of dt, because there is no length scale in the problem. Okay. I can use my same similarity variable as is. Okay. What about the total mass condition? Okay. The total mass condition was that, okay, at okay, boundary conditions at z C tends to 0 for z going to plus or minus infinity. Okay. And at t is equal to 0, C is equal to 0 for z not equal to 0. Okay. Initial time you are releasing the mass only at z equals 0. So, C is equal to 0 for z not equal to 0. Okay. And then I have this condition here that the total mass per unit area has to be equal to integral minus infinity to infinity dz times C. So, the z coordinate can be expressed in terms of the similarity variable. Okay. The z coordinate can be expressed in terms of the similarity variable. Okay. So, this becomes equal to integral, okay, d psi into root of alpha t, okay, into C, okay, because z is root alpha t times psi, therefore, dz is square root of alpha t times d psi. Okay. So, I can divide throughout by root alpha t, and I will get m by root alpha t is equal to integral minus infinity to infinity d psi times C. Okay. What do I scale the concentration by? Okay. So, at initial time the concentration is infinite at z is equal to 0, because I have released an infinite a finite amount of mass per unit area within an infinitesimal interval. Okay. So, the concentration goes to infinity, and far away the concentration goes to 0. there is no concentration scale in the system, in contrast to the previous example where we had a saturation concentration at the surface. How do we scale C? Okay. So, that C scaling is obvious from this equation. Okay. I can define C star is equal to C by m by root alpha t. Okay. M is mass per unit area, root alpha root dt. I am sorry, this is a mass diffusion equation. So, I should write this as dt. That will give me 1 is equal to integral minus infinity to infinity d psi times C star. Okay. So, that is the condition for the mass conservation. I scale the mass by m by root dt, and in the limit as the total mass concentration condition basically says that integral minus infinity to infinity d psi times C star is now equal to 1. Okay. So, these are the equations. Now, boundary conditions are, so the boundary conditions are that C star is equal to 0 for psi going to plus or minus infinity. Okay. And at initial time, okay, t is equal to 0, C star is equal to 0 for psi not equal to 0, because you are inserting it only at z is equal to 0 or psi is equal to 0, but it satisfies the integral condition. 1 is equal to integral minus infinity to infinity d psi times C star. Okay. And I have to solve the equation partial C by partial t is equal to d partial square C by partial z square. Okay. And I substitute from here. Okay. C is equal to C star into m by root dt into the equation. Okay. So, once again we differentiate by chain rule. Okay. So, I have here d square C by dz, sorry, dc by dz partial C by partial psi, I should write it as a total derivative. I know that C is equal to C star m by root dt. So, I get d by d psi of C star m by root dt partial psi by partial z. Okay. And in this the differentiation I can take out m by root dt. So, this is equal to m by root dt d C star by d psi, and partial C by partial psi is just equal to 1 by root dt. Okay, because psi is equal to z by root dt. Okay. Similarly, partial square C by partial z square, when I take a second derivative I get one more factor of 1 over root dt coming out. Okay. So, I will get this will be equal to m by dt power 3 halves d C star d square C star by d psi square. Okay. And then I have the derivative with respect to t, okay, which is equal to d by dt of C star by into multiplied by root dt. Okay. Note that C star is a function of xi and xi is a function of z. In addition, I have a time dependent factor here in the denominator. So, I have to differentiate this using chain rule. Okay. So, I will have plus C star partial by partial t of m by root dt. Okay. So, I have to expand this out using chain rule and then substitute that into the conservation equation and then solve for that. So, this I will continue in the next lecture. Kindly recall that we are releasing into an infinite medium, therefore, similarity solution applies. However, the condition is not that the concentration is a constant at a particular location, but rather that the total mass is conserved because it only diffuses, it cannot disappear. Okay. It only diffuses, it cannot disappear. Therefore, the total mass is conserved. Okay. Using that condition, I will show you that we get a slightly different equation and then we will solve that equation in the next lecture. I will see you then.